Good evening, everyone. Welcome to the week 7 live interaction session for the course Colloids and Surfaces. Let's just wait for a few minutes for others to join before we begin our session for today. So let me just present my screen. I hope my presentation is visible and I'm audible. Can anyone please confirm? Okay. So welcome everyone to the week 7 live interaction session for the course Colloids and Surfaces. This course is offered by Professor Basavraj from the Department of Chemical Engineering, IIT Madras. Myself, Pratyumnan, a PhD scholar from the Department of Chemical Engineering, IIT Guwahati, is one of the teaching assistants who conducts live interaction session for this course. So this week of week 7 of the course Colloids and Surfaces, we will be continuing our discussion on Gauss-Chapman model of electrical double layer. So we will be discussing more in depth on the concepts and different models of electrical double layer, and then we will be solving some of the numerical problems also. So as just as a recap to what we have done previously, again, we have built upon our concepts of colloids from the very scratch to understanding about the different type of interactions that are present in the colloidal systems. We have discussed about the van der Waals forces of attraction, and then the concepts associated with them, or the different type of interactions that constitute the van der Waals forces of attraction, like Keystone interaction, Debye interaction, and London dispersion forces. I hope everyone remembers those concepts we discussed somewhere in week 4. Yes. Again, after that we built on the we moved towards this models of the double layer models. So we discussed about the concept of formation of the double layer, and then the 3 different model associated with them. So can anyone tell me what were the models that we have discussed previously? Anyone? We have discussed one model, and then the second model is the Gauss-Chapman. So what is the model previous to this one? Anyone? So it is the Helmholtz model of electrical double layer, or it has its alternative name, that is the capacitor model. So that was the one that we discussed in the previous class, and then from there we went on deriving equations for solving some of the problems, right? So I hope you will be able to recollect the pictures A and B. So the first one here represents for the Helmholtz electrical double layer, or the capacitor model. So if you remember, over there we discussed about the formation of the double layer, where the counter ions, that is the ions that have the polarity opposite to that of the charged particles, and then we discussed about how these counter ions are closely associated, or get closely attached to this positively charged surface, result to make sure that the entire system gets neutralized. So there we discussed, so that model is known as the Helmholtz electrical double layer model. Then we came up with the more advanced model, where we incorporated the thermal diffusion that can happen in any liquid solution, or like in an electrolyte solution. So that Helmholtz model, one of the limitation was it didn't account for any kind of thermal motion that is present inherently in the system. So the diffuse layer model came out as a advanced model for the Helmholtz electrical double layer, with this thermal diffusion component incorporated within them. So over there we saw how the ions are near to the vicinity of the positively charged surface, are not exactly attached to the surface, but they are present near to its vicinity, and due to the thermal motions they are and due to the thermal energy they exhibit their own diffusive motion. So that's what you can see from picture B. Here you have the negative ions, and also, apart from the negative ions or the counter ions, there will be co-ions also present. in the solution or the positive cations. So those ions will also be present not in a higher concentration, but at a lower concentration they will be present near to this positively charged surface. So if you see, this is the this two graphs actually depict the variation of your potential with the distance. So in case of Helmholtz electrical double layer model, since they are very close to each other, the counter ions and then the surface, since they are very close to each other, the variation in the potential with respect to the distance is given like a linear, is like varies linearly. The potential with respect to the distance varies linearly. Whereas in case of the diffusive layer model, if you see, that variation with the potential variation with the distance is exponential. It decreases exponentially as we go far away from the surface. So these were the two models that we discussed previously in the last live, in the last to last as well as the last live interaction session. And then we also discussed about the mathematical models for both the Helmholtz electrical double layer and then the diffusive layer model. So we, in the last class, we derived the first one, the Debye-Huckel approximation, where the psi, that is your surface potential, where psi, that is your potential, is related to the surface potential psi naught and the distance at where you want to calculate the potential, that x. So we saw how does the your potential varies with the distance as we move away from the particle or the surface. So this Debye-Huckel approximation came up with a certain like we derived this equation the using a particular approximation or using the Debye-Huckel approximation, where we told that the potential is very low, is low. So truly the name for this was the linearized Boltzmann equation. So we derived the linearized Boltzmann equation, and for that linearized Boltzmann equation we gave a particular condition where, and then simplified our solution, where we stated that that particular assumption, what we stated was that the potential should be low. So this is how we came up with this relation of psi equals psi naught e exponential minus k, minus kappa times x. So kappa is nothing but it is your Debye-Huckel parameter. So once we are done with this, in this live interaction session, we will be discussing about what to do if your psi value is not low, like if the surface potential is high. So in that case, we cannot, if your surface potential is high or is very high, then we cannot use this approximation. So for that, we need to derive a more generalized expression. For that, we use the linearized Boltzmann's equation, and then we did many mathematical manipulations to that equation. At the end, we derive this relationship. Psi equal, so you can say gamma equals to gamma naught times exponential of minus k, kappa x. So this also tells you the relationship between this gamma and x, or how your value of gamma is going to vary with x, or more appropriately you can say it as how your potential is going to vary with the distance from the surface of your interest, provided that the potential that you are uh, looking up is very high, or that you are considering is very high. So that is what was with the Gauss-Chapman's model, where we evaluated the potential of the surface without really, you can say, without really having a condition of low surface potential, unlike in the previous derivations. So this gamma was given as exponential ZE KT. Exponential ZE psi by 2 KT minus 1 divided by exponential minus Z, that is Z is nothing but it's a valency of your electron, or sorry, valency of the ions that you're considering here. So this is your value of gamma. So this is with your Gauss-Chapman model. Now, with these two models, you also have a third model, which is some sort of like more kind of an elaborate model for the electrical double layer concept. So in that model, what is the incorporation is that it's just the combination of both your Helmholtz model and the Gauss-Chapman model. So that's what something you can see here. You have a, if you see the variation of the potential with respect to the distance away from the surface, so up till stern layer, if you see, it is, or up to this position, if you see where my cursor is pointing, you can see that the potential is decreasing linearly. Then after this particular distance, if you see, the potential is decreasing exponentially. So this is something like more of a, the third model is more like of a combination of your first model, that is your Helmholtz or the capacitor, and then that of your diffusive layer model. So the place up to which, so this is the third model, and then the place up to which the potential is going to linearly vary or linearly decrease with the distance, that particular layer is called as the stern layer. And after your stern layer, you have your diffusive layer, just like in this case. And after the diffusive layer, since the effect of the surface is not uh, very prominent after a certain distance, so here it will be just the bulk without any, it does not have much of its potential. So this will be in case of the bulk. So this potential that you see in the stern layer here, where there is a transition from the stern layer to the diffusive layer, the point or the place or the point, at that point the potential is called as a zeta potential. And beyond this, that is your diffusive layer, that potential is called psi d. So beyond psi d, there will not be much of the effect of the, or there will not be any kind of potential due to the particles, or you can say that the charge surface will not have any effect after that after that layer. Let me just mention that. So the potential here is psi d, and then the potential here is the zeta potential. Of course, we have discussed the concept of zeta potential in week 2 or week 3 live interaction session also. But even after this, we will be discussing in the next live interaction session more about this concept of zeta potential. But for the time being, it is better to just understand or remember that the potential difference between the stern and the diffusive layer, or this particular position where there is a transition from the stern layer to the diffusive layer, that place the potential is called as the zeta potential. So that's about with the third model, which is nothing but is a combination of both the Helmholtz and the Goy-Chapman model. It's like more of an elaborate model, as I said previously, which kind of takes under the consideration of both the linear as well as the, or of both the Helmholtz and the Goy-Chapman model. So next, after this discussion on the three layers of the model, next what you have is something called as the repulsive forces between the two flat surfaces, or to be very or to generalize, you can say it is the interaction that is usually present between two flat surfaces. So the interaction that is present between two flat surfaces. So for this, so here you can see you have two flat surfaces, and both the flat surfaces has the surface potential as psi naught. So here we have taken the flat surfaces, both the flat surfaces to be of similar chemical composition. So both flat surfaces are of similar chemical composition. So that is due to which they have the same surface potential on either side of their surface. So if you see here also at this corner or at this end, the surface potential will be psi naught, and similarly towards this area also the surface potential will be psi naught. So when these two surfaces actually interact with each other, so this usually happens only when the separation distance, that is your delta, is less than kappa inverse. So I just said now what is kappa, that is the Debye-Huckel parameter. So can anyone tell me what is kappa inverse? Last class also we discussed this. What is kappa inverse? Anyone? So it's simple. I mean, we have done a lot of questions, previously in the last class also regarding this kappa and kappa inverse. So kappa is Debye-Huckel parameter. So what is kappa inverse? Anyone? What is kappa inverse? So kappa inverse is nothing but it is the Debye length. So please remember this. Kappa is your Debye-Huckel parameter and kappa inverse is nothing but Debye length. So previously also I told this that if you are unable to remember, just remember the units. So unit of kappa is meter inverse and units of kappa inverse is meter. So if you just remember K as meter inverse, then K inverse will be nothing but meter. So when we say something is Debye length, which actually means that it has a units of length, so that will be meters. So from there you can say that kappa inverse is nothing but is same as that of the Debye length. So this is just like if you are unable to remember, but please remember that kappa is the Debye-Huckel parameter. 1 by that of kappa is nothing but is your Debye length. So coming back, so this repulsive forces that actually acts or some sort of the interaction between these two flat surfaces is only applicable or is only possible when the separation distance between the flat surface is less than kappa inverse or is less than the Debye length. Because once the flat surfaces are separated by a distance larger than the kappa inverse, then there will not be much of an interaction between, or there will not be any kind of an overlap or interactions between the two flat surfaces. So this distance of separation is an important parameter. I hope you are able to get it. If not, please let me know, because based on this we'll be solving few problems in the next 1 hour or so. Again, there is internet connectivity. Sorry, there was a network issue. So yes. So where were we? Yeah. So I was just asking if anyone has any doubts related to what we are discussing now on, especially this, this where your separation between the concept of separation distance and your Debye length. So please let me know now. Anyone? Okay, so that is what we were so, which means that if your, let's say, the separation distance is more than k inverse, or is more than uh, you know the Debye length, then in that case what actually will happen is that there will be no overlap of the electrical double layer, or the two layers that you are going to have will not, their potential, the potential profile or the double layer will not interact with each other or will not overlap with each other. The kind of forces of kind of that forces of that interaction forces will not be present, so that repulsive forces that will be, between the two surfaces will not be present. They will be acting more like an two independent bodies which have no effect on each other. So that is the reason why this particular condition should be applicable. Then only you can actually discuss about the interaction of the two flat surfaces, and then the overlapping of the double layer will happen only when your separation distance is less than the Debye length. So when you talk about this repulsive forces or the interaction, it is actually due to uh two forces are actually contributing to this. So one is nothing but is your osmotic pressure, and then the other one is the electrostatic repulsive forces. So these two flat surfaces, I forgot to say, are actually present or are present in a particular electrolyte solution. So what usually happens is the concentration of the ions will be greater in a region between the flat surfaces compared to the other surface. So let's designate this as inner region and this one as outer region. So the concentration of the electrolyte ions or of the ions, let's say it is C1, and let's say this is C2. So the concentration of the ions in the inner region will be greater compared to the concentration of the ions in the outer region, or you can say your value of C1 will be greater than C2. Due to this differences in the concentration of the ions between the inner and the outer region, there will be an osmotic pressure. So osmotic pressure is due to the difference in the concentration of ions between the inner and outer surface. So this is one. So this is the possible driving mechanism for the reason of osmotic pressure. Since the ions are present, there will also be the electrostatic repulsive forces. As I said, both the flat surfaces are of similar chemical composition. So the ions that will be surrounding these flat surfaces will also be of the same nature. So due to this, there will be the electrostatic repulsive forces. So these two forces together contribute for the net interactions that will be present between the two flat surfaces that you are taking under consideration. So the negative charges, oh sorry, the charged particles of similar polarity, or you can say of similar nature, will result in the repulsion or will contribute to the repulsion. So these are the two forces that are contributing to the what do you say, the for the forces of attraction between the two flat surfaces, or I'm sorry, you can say that these are the two forces that are contributing to the interactions between the two flat surfaces. One is your repulsive and the other one is your osmotic force. So together you can actually write this as or the osmotic pressure, and then your repulsive forces as 64K, that is your Boltzmann's constant. It's not kappa, it's Boltzmann's constant, times T, that is your temperature, times N infinity. I hope everyone remembers what is N infinity. Any response from your side? What is N infinity? N infinity. Last class we have solved numerous problems and we have also discussed this concept of N infinity. Of course, not numerous problems, but we have discussed this concept of N infinity. So, if you remember, we discussed about this kappa square is equal to E square by epsilon naught kt times sigma zi square ni infinity. So, we discussed and we solved problems also. So, what is N infinity is? N infinity is the concentration of the ions at an infinite distance from the surface, or you can call that as a bulk concentration of the electrolyte ions. So please remember, try to remember these expressions, because you will be solving problems and there you will be requiring this times tan h square Ze phi psi naught by 4 kt into e power minus k times delta. So here, for a simplification, I have done this. So if you see here, so your psi is nothing but, it is, you can write this Ze psi by 2 kt as x. Let's take it as x. So you can write this as exponential 2x minus 1 divided by exponential 2x plus 1 minus 2x plus 1. So can you write this as tan h of, let's take Ze psi by 2 kt as x, and this also has x minus x. Can you write this as tan h of 2x plus tan of 2hx, or tan h of 2x? Anyone, any ideas on that? Can you write this expression e power x minus 1, or e power x minus 1 divided by e power x plus 1 as tan h of 2x? Anyone? I mean, whether am I writing it correct? Oh, again, there is an internet. So this is how you will, what do you say? You can actually write this expression as the other way, or you can also make it as gamma square exponential minus k delta. So that is, your convenience. So let me just write that expression also. So that is nothing but Fr equals to 64 k t n gamma square exponential minus k times delta. So this is another way of, uh, you know, I mean, this is the way which is actually described in the video lectures. But again, if you want to simplify, then you can go with the above expression also. It's just that I have manipulated it to make it appear similar to tan h square. But yeah, it's up to you to which whenever is easy for you, you can use that one. So yes, this is about the electrostatic forces. Then we have the DLBO theory. So in the DLBO theory, there we discussed about the interactions. Over there, we discussed about that how both the van der Waals forces of attraction, that how the DLBO theory considers both these repulsive forces and then the van der Waals forces of attraction with each other for with each other when determining the interactions between the two particles or two surfaces. So this is about today's concepts. So let's just go on to problem solving session. So yeah, before that, if you see here, this dotted lines are actually the way the potential actually decreases in this interactions between the two flat surfaces. The dotted lines represents the way the potential actually decreases with the distance. But when the separation distance is less than Debye length, in that case what usually happens is that the double layer overlap with each other. There is a interactions between the two potentials, and these interactions, when you plot that as a function of distance or as a function of the separation distance, you get a curve which is something that is what is represented through a solid line. So it looks more like a parabolic graph. So you here on both the sides you have sigma naught, and at x is equal to delta by 2 is your what do you say, is called as psi of delta by 2, and that is what governs your interaction or the potential between the two flat surfaces. So that minima of what you see is the governing, or that's what governs the, or that is the potential that governs the repulsion between the two flat surfaces. gamma uh, gamma at delta by 2 governs the repulsion between governs repulsion between two flat surfaces. So this minima position, that is the place where the which actually governs the repulsion between the two flat surfaces. So now moving on towards the question. So if you have any doubts, let me know, or otherwise we can, move for other questions. Anyone? Any questions? Because these concepts will be useful for your assignment solving. So that is the reason we are discussing this, and also this will be useful for your exam, which is coming up soon. Anyone? Anyone? I mean, there was a echo. Okay. So if you have no doubts, then I think we can go for solving the problems. Okay. So this question is similar to what we have done in the last class also, but again, we will try solving more of these problems, which will be like, useful for you. So the question one is, consider an aqueous solution containing asymmetric electrolyte. Again, I hope you guys are able to recollect what is asymmetric electrolyte and symmetric electrolyte. So symmetric electrolyte is nothing but it is where both the valency of both your cation and anion will be the same. But in case of asymmetric electrolyte, both the valencies of the cation and the anion will be different. So That is what you can see here. The asymmetric electrolyte is of type 3 is to 2. That is, your cation is 3 and anion is 2. At zero point 0.1 molar concentration, the useful quantities, that is charge on the electron is given, epsilon naught is given, dielectric constant is given, temperature is given, and Boltzmann's constant is given. They are asking us to estimate the Debye-Huckel parameter and the thickness of the double layer. After that, they are asking you to calculate the potential at a distance of 2 nanometers and 30 nanometer if the surface potential is 30 millivolt. So I think the part A will be easy because it's something that is what we are solving, what we solved previously also. Only the question B is different. So please solve it and let me know the answer for part A. Then we will progress to part B. Please solve and let me know. So how do you progress with this? The first step. So what is Debye-Huckel parameter? Just now I said, right? So your kappa is called as the Debye-Huckel parameter and the thickness of the double layer is nothing but inverse of that kappa. So let's start solving. But meanwhile, you also solve and let me know because I guess last week we did approximately 5 questions related to this calculation. So by this time, you should have been like a bit, you, you will be a bit proficient now. But anyway, So let me just use the expression from there. So this was what was your kappa square. So using this, let's calculate. So kappa square is E square times. So first for calculating the kappa square, let's calculate the summation of zi square ni infinity. So, so summation of zi or summation of z square times your ni infinity. So what will be this value? So you have both cation and anion. Cation is having 3 valency and anion has having 2 valency, and your Ni is 0.1 molar. So that will be nothing but plus 3 plus 3 the whole square times 0.1 plus anion will have negative charge, so minus 2 whole square times 0.1. So that will be like 0.9 plus. So it is nothing but 9 times 0.1 plus 4 times 0.1. So 0.9 plus 0.4. So that will be 1.3. So this is the Zi square Ni infinity term value. Now let's calculate the rest. That is your E square by epsilon naught times k t. So E square is 1.6 into 10 to the power minus 19 the whole square. This divided by epsilon times epsilon naught. So yeah, epsilon naught is 8.85 times 10 to the power minus 12. This times your, and this is epsilon naught value. Value of epsilon is nothing but dielectric constant, that is given as 78.54 times K, that is your Boltzmann's constant 1.38 into 10 to the power minus 23 times T, and that is given as 25 degrees Celsius. So when you take it in terms of Kelvin, it will be 298. So what will be the value for this? Let me just use my personal calculator. Please calculate the value and let me know. So yeah, there was a internet disruption. Actually, the weather over here is quite not rough. Uh, so that is the reason there was a network disruption for a few minutes. Okay, so we started with question number one, where it is again. Let me read it loud so that we can start solving this once again. We have taken an aqueous solution containing asymmetric electrolyte of the type 3 is to 2 at zero point 0.1 molar concentration. The useful quantities are given to you, and then they have asked us to calculate or estimate the Debye-Huckel parameter, that is your kappa, and the thickness of the double layer, that is your kappa inverse. After this, they have asked us to calculate the potential at a distance of 2 and 1 nanometer and they have asked to us to take the surface potential as 30 millivolt. They are asking us to calculate this potential based on the Debye-Huckel model. So this is the equation that we use to calculate the value of kappa. So as I said today also, that we have solved a number of problems in the last class based on this. So let's just solve this question for today. So first let me calculate the quantities under this sigma bracket. So that is nothing but z square. Okay. So is my presentation visible? Anyone? Yes, visible. Okay. Okay. Thank you. Z square, that is, sorry, z square times ni. So which will be nothing but, so here we talked about this previously also. So this Ni is nothing but the concentration of the ions, but it is uh, the number of ions per unit volume. But the concentration of the ions, if you see here, the units is in terms of molar. So we need to convert this Ni in terms of Ci. So for that we multiply. So for that the conversion factor is like, it goes somewhat like this. So it is Ni is nothing but 1000 times your Mi, that is your molarity. Here it is 0.1 molar times Avogadro number. So we can take this 1000 and Avogadro number outside of the sigma because they are constant quantities, and just evaluate this Zi squared times Mi. So let me change this. You can take Mi or Ci because in the last class we took Ci, but in the course it is given as Mi. So for convenience, let us keep it as Mi. So this will be nothing but what it will be. So first is for, let's say, for cation. So it will be plus 3 whole square times your molarity, that is 0.1. Similarly for the anion. So for anion, the charge will be negative. So minus 2 0.1. So the value is, what is the value? 3 square is 9. 9 times of 0.1 is 0.9 plus you have 0.4. So this value is nothing but 1.3. Now we need to evaluate the parameters which are outside this sigma bracket. So that is nothing but, last time also we calculated this. This is just for practice purpose. We are doing this once again. So please solve it along with me so that it will be easy when you do your assignment problems. So it is 1.6022, that is nothing but your E, times 10 to the power minus 90. So this whole square times, now you have this Avogadro number. So Avogadro number is 6.023. If you have solved and you have the answers, please let me know. So this is the numerator divided by the denominator. So in denominator you have epsilon naught. So epsilon is the dielectric constant. So 78.54 times your epsilon naught. So epsilon naught value is given as 8.85 into 10 to the power minus 12 coulomb square per Newton meter square. Times K, that is your Boltzmann's constant, 1.3807, times your temperature, that is 298. Yeah, 25 degrees Celsius, so that is 298. So what was the value? Last week also, if you remember, we calculated this value. That is, if your dielectric constant is going to be 78.54 and your temperature is going to be 25 degrees Celsius or 298 Kelvin, the value came out around 5.05 times 10 to the power 15. I hope you can recollect what we did in the last class, because the part A is same as what we did previously also. It's just that to have a practice, as I said. So your kappa square will be this 5.405 into 10 to the power 15 times, just a second, we forgot to, yeah, here it is, times 1000 times 1.3. So what will be the value? So let me just check it in my calculator. Please let me know the answer if you have solved already. Yes, any answers? So please check this calculation also for us to verify whether we were correct at that time or some other uh, changes is there to this value. So this value will be nothing but 7.028 into 10 to the power 18 meter power minus 2. So the value of kappa is nothing but root of this. So just a second. So 7.028 times 10 to the power 18.5. So it comes around 2.65 times 10 to the power 9 meter inverse. So 2.65 times 10 to the power 9 meter inverse. So this is your Debye-Huckel parameter. Debye-Huckel parameter. So your kappa inverse is nothing but is your Debye length. So this is nothing but 1 by this value 2.65 times 10 to the power 9. So this value is nothing but, let's calculate. What is this value coming around? Anybody? 3.77 times 10 to the power minus 10, or you can simply say 0.37 nanometers. So your Debye length or the thickness of the double layer is nothing but 0.37 nanometers. Now we are asked to calculate the potential at a distance of 2 nanometers and 1 nanometer, and they are saying that the surface potential is 30 millivolt, and calculate this according to the Debye-Huckel model. So let me let me go to a next slide. So that will be like psi, that is the potential at where you want to calculate your I mean, yeah, there's the potential at a particular distance x. Time is nothing but it's equal to psi naught, which is the potential of the surface, or the surface potential that you're taking under consideration. So psi naught times exponential of minus kappa times x. So here x is first given as 2 nanometers. Surface potential is 30 millivolts. So let's keep everything in millivolt first. So I'm just going to write 30 times exponential of kappa. So minus of kappa. Kappa value is nothing but 2.65 times 10 to the power 9 meter inverse. So 2.65 times 10 to the power 9 times your x is nothing but 2 nanometers. So that is 2 times 10 to the power minus 9. So 10 power 9 and 10 power minus 9 will get cancelled. So that will be nothing but 30 times exponential of 2 points minus here also minus 2.65 times 2. So that will be nothing but uh, minus 5.3, and exponent of minus 5.3 is, so the value is 0.0049, or yeah, you can say 499. So let me write 0.00499 millivolt. So you can see here that the potential at 2 nanometer distance is very less. So this is probably because of the fact that the surface potential has an effect only up to the Debye length. Beyond the Debye length, the potential decreases rapidly, and it reaches to a extent where the value is very minimal. So that's what is predicted from this graph if you see. So at the surface, the potential is maximum, that is psi naught. And as you keep moving away from the surface till the end of diffusive layer, the potential keeps decreasing, decreasing, decreasing in an exponential fashion. And after the Debye length, or after crossing this diffusive layer, the potential drops to its lowest value, and after that crossing, the potential remains constant. There is no change in the potential, but the potential has reached its lowest level. So that's what we can see here mathematically. If you see, our Debye length is 0.37 nanometers. but we were asked to calculate what will be the potential at 2 nanometers. So if you see here, the potential is 0.00499. So you can see how small the value has reduced. So only the value will be considerably high in the region before the debye length. After that debye length or after that diffusive layer, once we start focusing on regions greater than or with a distance that is greater than the debye length, then there the potential will be very less. So this is some math, you can say it is a mathematical way to uh, help us get convinced that yes, what we are saying is right. So similarly only will be the possibility if in case of what do you say, just a second. Similarly, if you take at x equals 1 nanometer, still this distance is going to be greater than your debye length. So your potential at 1 nanometer distance from the surface will be nothing but surface potential times exponent of minus 2.65 times 10 to the power minus 9 times 1 nanometer. So I'm going to write this that one as 10 power minus 9. So this will be plus 9. So this is nothing but exponent of minus 2.65. So that will be 0.0706. So 30 times 0.0706. So that will be nothing but 2.119. So 2.119 millivolt. If you see here, we forgot to multiply by that 30. So that's a mistake. So please correct that. So then that value will be 0.00499 times 30. Yeah, just a second. Let me recalculate this. So yeah, this times 30. This is 0.1497. Anyway, so if you see that at 1 nanometer, the value of surface potential is 2.119. But if you see at 2 nanometers, the value again decreases to 0.1497. So that decrease keeps happening as you keep moving away from the surface. Suppose, for example, let's say I'm going to take a region which is inside the diffusive layer or the debye length. Let's say, for example, x. Let me mark this as 1. Sorry. Case 1, case 2, and let this be case 3. So here, let x be equal to 0.2 nanometers. So then in that case, if you calculate your surface potential, if you calculate the potential at 0.2 nanometer distance from the surface, then it will be 30 times exponential minus 2.65, that is your kappa value, times 10 to the power 9, plus 9, times 0.2 nanometers, that is 2 into 10 to the power minus 10 meters. So what will be this value? It will be exponent of minus 0.53. Point 0.5886, this times 30 will be 17.658. So you can see at 0.2 nanometers, the potential is 17.65. But once you cross that Debye length or that diffusive layer, the potential is very less, like 2.11, and at 2 nanometers, it goes to 0.1497. So if you keep progressing further away from the surface, then the potential value will keep lowering, and after a considerable distance, let's say of around after a considerable distance, the value will, remain very less, like it will be like 0.00, some values will start to appear. So this is how it's just you can take it as a validation, or we are mathematically trying to understand how does the potential decay as we move away from the surface of the surface of the uh, particle, or you can so you can take the surface of the particle. So are there any doubts related to this? Because we may not be solving this Debye-Huckel parameter questions again. So if you have any doubts, please let me know, or otherwise we can go for the next two numericals. Any doubts? Okay, okay. So next question is, they are asking us to calculate the electrostatic double layer repulsive forces between flat surfaces in aqueous magnesium sulfate solution. Concentration is given as 10 mole per meter cube and separation is given as 1 nanometer. They are asking us to calculate the surface potential is given as 100 millivolt and the temperature is given as 298 Kelvin. Now here they are asking us to calculate the electrical double layer repulsive forces. So if you see this one, the repulsive forces between the two flat surfaces. If you remember, we just now discussed this concept of repulsive forces. So based on that, we have a question to solve. So here they are asking us to calculate the, what do you say, the electrical double layer repulsive force. So the value of Fr. So let me just give you the expressions I have previously in one slide. So since these expressions are quite difficult to type, I have written it previously. I hope it is visible. Is it visible? The equations? Yes, visible. Okay. So so this is the equation where Fr is nothing but 64 times kT, that is K is your Boltzmann's constant, T is the temperature, N infinity, that is the concentration of the ions in the solution, gamma square exponential of minus h, or you can say delta, that is your separation distance, and divided by Debye length or kappa inverse. And then your value of gamma can be given as exponential of this Boltzmann's factor by 2, that is Ze psi by 2 kBt minus 1 by exponent of Ze psi by 2 kBt plus 1. So you have the value of so once you know this Boltzmann's factor or Ze psi by 2 kBt, you can calculate the value of gamma, and you know k t n infinity psi square, you need to calculate the Debye length, and if you know these quantities, then this question will be easy to solve. So please solve this. Let me just wait for a few minutes. So meanwhile, let me just write down the parameters. So magnesium sulfate, that will be nothing but Z value will be 2. It's symmetric. So I had previously calculated the value of kappa inverse, that is your Debye length. Let me just give that Debye length to you, and please verify and tell me whether that the same. Is it the same as what you get? So this will be your Ze psi by 2 kBt. So Z value, as I said, is 2. E is electron charge, 1.6 times 10 to the power minus 19 coulomb, times your surface potential, or your psi, that is 100 times 10 power minus 3. So here this sigma what you see will be sigma naught. So that is the reason you can take here it as omega naught. Sorry, not omega, psi naught. So I have given this as sigma. So here this sigma represents for the what do you say? So this psi is psi naught. So this sigma will be sigma naught. So then this value. So if you calculate, did anybody calculate this value to the ZD psi by 2 kBT? Any answers? So the value is around 3.88.
Yeah, like that.
Okay. So exact value is 3.8887. This one, yeah. So I hope all of you got this value. Since I received one answer from the attendees, so I'm going to take this value as 3.8887. So this is your ZE psi by 2 kBT. So the value of gamma will be, we need to calculate. So let me calculate the value of gamma. So gamma will be exponent of ZE psi by 2 kBT, that is this 3.8887. So 3.8887 minus 1 divided by exponent of 3.8887 plus 1. So the value of this is just a second. So this is the value of e power 3.8887. So 48.84. 48.84 minus 1. Same value 48.84 for the bottom also. So plus 1. So that is nothing but 0.9598. So this is the value of gamma, 0.9598. So similarly, then the value of gamma square or gamma naught square will be nothing but square of this value, 0.9598. So that is going to be 0.9212. So this is the value of gamma square. So now you have the value of gamma square, you have K inverse. So it's just about substitution. So your value of Fr is nothing but. So here again n infinity is there in the equation, but here we are given C, that is your concentration, or M, molarity in terms of mole per meter cube. So so concentration is given in terms of mole per meter cube. So we need to replace this with n infinity here. So if you use the previous expression, you can modify this as 64 times R times T times again gamma square times exponent of minus h by k inverse, because if you take here, sorry, I forgot the c, because if you see n infinity can be written as c infinity times Avogadro number, and k can be written as r by na. So let me write that as k is nothing but your Boltzmann's constant. K can be written as R, that is your universal gas constant, by Na, Avogadro number, and your N infinity can be written as Na times C infinity or C. So if you just substitute this in this equation inside this box, then your Na will get cancelled, and what you will be left out with this R and C, that is your universal gas constant and concentration of the MgSO4 solution that you are considering here. So that's how I wrote the equation as 64 RTC gamma square exponent of minus H by kappa inverse. So repulsive force will be nothing but 64. Gas constant, I hope everybody will know, 8.314 times, oh sorry, your T, 298 Kelvin, times concentration, that is 10, times your gamma square, so 0.9212, times exponent of minus H separation distance, that is 1 nanometer, by your kappa inverse, so that is 1.52 nanometers. So we need to evaluate this. So let's calculate 1 by 1.52 is minus 0.6589 or 0.6589. So exponent of 0.6589 is 0.5174. So FR is nothing but 64 times 8.314 times 298 times 10 times 0.9212 times 0.5714, yeah, 0.5174, sorry. So what will be the value of FR? It's nothing but 64 times 8.314 times 298 times 10 times 0.9212 times 0.5174. So it comes around 755.764, sorry, 755, sorry, it is 7,55,764.715 Newton, or you can write it as 755.716 kilonewton. So this is the repulsive force. So this is how you calculate the electrostatic double layer repulsive forces between two flat surfaces. And if you see here, the distance of separation that we are going taken here is 1 nanometer, which is lesser than your Debye length. So since, if you remember this expression, it's applicable only when this separation distance delta or h is less than k inverse. Then only both the surfaces we can consider them as interacting surfaces, and due to which there will be a repulsive force because of the interaction. That is the interaction that happens, that is present between the flat surfaces, repulsive in nature, and we can calculate what is the repulsive forces acting on it. Now, so this question number 3 is also very similar to what we have solved here. Same expression and everything remains the same. So before this, let's solve this problem and then we will come back to question number 3. So question number 4 is nothing but calculate the net interaction energy for two planar surfaces at 298 Kelvin if your psi naught values 100 millivolts and 20 millivolts. So here you have two different cases. One case where you are going to consider your surface potential as 100 millivolt, and the second case is where you are going to consider your surface potential as 20 millivolts. We have the Hamakers constant value as 1 into 10 to the power minus 20 joules, and concentration is given as 10 mole per meter cube, and this is present in a 1:1 symmetric electrolyte. So we are asked to calculate the net interaction energy. So if you remember, net interaction energy is nothing but it's a combination of two, right? So one is your electrostatic, the double layer repulsive forces. What is the second one? Anyone who knows what is the second one? There are two. One energy is something that is related to your electrostatic repulsive, and another one, what do you say, term, like it's a contribution of two different types of energies. What is the second one? Yeah, so that's correct. So let me just write that, give that expression here. So your net interaction energy is nothing but it's sum of this electrical double layer repulsive forces and the van der Waals forces of attraction that exist between two planar surfaces. So these two interactions will together make your net interaction energy. So that expression is given as, so phi of this ideal or electrical double layer repulsive forces is given as 64 kT kappa inverse psi square exponent of minus h by k inverse. And the van der Waals, if you remember from the week 5, week 6 live interaction session as well as the lectures, that expression is nothing but for a flat surface, it's minus ah by 12 pi h square, where ah is nothing but your Hamakers constant and h square is nothing but the separation distance. So, just a second. Here we have to calculate the net interaction energy profile. So we need to. It's not about calculating what is the value of net interaction energy, but we need to calculate how your net interaction energy is going to vary with the distance between the planar surfaces, and that too for two cases. So we need to first write the expression in terms of the separation distance h for both the cases. Then we need to vary the value and then find how the interaction energy is going to vary with the distance. We need to see the profile. So for that, I have some expressions previously to calculate. So if you consider your surface potential, first case for surface potential as 100 millivolt, then we need to use this expression and then calculate. So what are you going to get? So again, the same way to calculate your gamma naught, we use ZE psi naught by 2 kBT. Here the electrolyte is 1:1, so the value of Z is 1. So if you do this, your value is of this particular expression will come out around. So we need to first calculate the value. Just this calculation, let me do it in my personal calculator. Meanwhile, if you have the answers, please let me know. So this value is nothing but 1.9453. So this is your uh, answer for this particular expression. So once you know this, you can calculate the value of gamma. So gamma is nothing but exponent of this minus 1 by exponent of this plus 1. So let me just so it is 6.9957 minus 1 by 6.9957. plus 1. So the value is nothing but 0.749. 0.749. So this is your gamma. So gamma square will be nothing but 0.75 square. That is 0.5622. 5622. So this is your value of gamma square. So now once you get your value of gamma, we need to find kappa inverse. So let's do that also. So kappa inverse is nothing but, so first we need to find kappa square. Then from there we need to find uh what do you say? Again, as I it goes off like this. So first you need to find what is the value of this summation, then multiply this factor, that will be kappa square, then you take the square root, you'll get kappa, and then from there you can get kappa inverse. So this value I have previously calculated as, since we know this, I'm not going to show the calculation here, I'm just going to take it out. So this value is nothing but 3.04 nanometers. So please calculate this, since I have previously calculated, and we have also done multiple problems on calculating Debye length and Debye Huckel parameter. I'm just going to write this value as 3.04 nanometers. So you know gamma square, you know kappa inverse, and you just now need to substitute and get the generalized expression, or get the expression in terms of H. That is nothing but net interaction energy. Net interaction is nothing but 64 times, again that R, everything will what do you say, will become, sorry, k and c will be, k and n will become R and C here, as I explained in the previous problem. So it is 8.314 times 298 times, you have your kappa inverse value, so that is 3.04 times 10 to the power minus 9 times your C, that is 10. So this times exponent of, so so it will be minus h by kappa inverse, so 1 by 3.04 nanometers. So if you take the reciprocal, it will be 0.329 times h minus your Hamakers constant, so that will be 1 to 10 to the power minus 20 by h square. So this is the net interaction energy of your two planar surfaces which have the surface potential of 100 millivolt in 1:1 electrolyte with a concentration 10 mole per meter cube. Similarly, for, oh sorry, this is 20 millivolt. So similarly, the expression for psi naught at 20 millivolt will be nothing but net interaction energy is equal to I'm just going to write the expression here. So this comes out around point 001038 exponential of minus 0.3298 times h minus 10 to the power minus 20 by h square. So this is for oh, by 12 pi times 10 to the power. Okay, see. So this is a by 12 pi h square. So you will have 12 times 3.14 times h is in nanometers. So we are going to take that out. So it will be 10 to the power minus 18. And this, the units will be joule per meter square. So if you simplify this, okay, let me finish the expression here. So if you simplify that, you will be getting one, just a second. So you'll be getting 0.000265 h square. So this is how your net interaction energy will vary for psi naught as 20, and for psi naught as 100, the expression will be point 0.0027211 times exponent of minus 0.3298 h minus, so these are the respective equations. Yeah. So now we have the equations with us now, and we just need to calculate how this is going to vary and plot the profile. So for that, I'm going to take my Excel sheet here. Just a second, there is a small error. So similarly here also it will be. So this is how it is. This is the expression. So if you use this expression, and then let's calculate what will be your H for the respective potential values. So if so this is your psi net value, or I mean the net interaction energy at h equals 0.5. So if you do this, and if you do for other values of h also, you will get the values, their respective values. And similarly, let's do the same thing here. So this is their respective net interaction energy. So if you plot these two profiles, let's take the value of h here, and this will be at net 100 millivolt, and the next one will be, so this, just a second, there is some issue. Oh, okay. So let me just try with this way. Let's plot this graphs. So this is the plot. So if you see, so this is your, the x-axis is going to be your h, that is the separation distance, and your psi net is going to be your y-axis. So if you do for other smaller values, then you can have more data points and then you can get the curve. So what we just need to know here is, or based on this curve, what you can observe is, if you see, with the increase in the surface potential, your energy barrier, that is this point, if you see this data point at psi equals 1, that energy barrier is going to increase. So so that energy barrier is something that actually, uh, what do you say, is something that is going to determine whether your system is going to be stable or it is going to undergo some coagulation. So if your energy barrier is less, then the likely chances of the colloidal dispersion to undergo coagulation will be more. If your energy barrier is more, then the likeliness or the likelihood of your colloidal suspension going to be stable is more. So with the increase in the potential, the energy barrier is increasing. So which means that the system is going to be more stable at higher potential compared to the lower potential values. So this is, if you remember, even in the course also we have discussed professor has discussed regarding this. So this is just again we are further solving problem and then verifying whether, and then just understanding that concepts more properly through solving problems. So this is with today's lecture. So if you have any doubts, please let me know. This question is something where you need to calculate the excess pressure, and then this is exactly the same as this one, except that you need to it's exactly the same thing. So I don't think there will be a much difficulty while solving that problem. Let me just paste this. So if you have any doubts, please let me know. So any doubts, or can we conclude the session here? So if there are no doubts, then let me just conclude the session here. Of course, you are always welcome to email me. My email ID will be present in the presentation slides that will be shared. So I thank all of you for joining today's session from 5 p.m. to 7 p.m. Our next live interaction session will be on next Sunday, that is on 15th of September from 5 p.m. to 7 p.m. I hope to see you there. I thank Professor Basalraj as well as the NPTEL team for providing me this opportunity to interact with you all today. So let's meet next Sunday for our final live interaction session for week 8. Till then, bye.